Hello everybody and welcome to ECMath. Today we're going to recap something we talked about in class as well as talk about the classwork problems. I'm recording this from school. I'm not going to really edit this video down. It's going to be more like a live stream that you can watch just if you need to go over the classwork. I'd encourage you to jump to the problems that you need to jump to. I'll try to put timestamps down below. But first, a recap on section 2.6, just in case you need it. We're looking at rational functions, which are functions that look like this. They might not be factored, but your first job would be to factor them. Then once they're factored, you look for any factors that simplify out, and those factors will create holes. So when I see an x minus 3, that's saying there's going to be a hole at x equals 3. To find the y-coordinate of the hole, you take the simplified version, which is 2x plus 1 over x minus 2, and you input 3 into that equation. So this would be 2 times 4 over 3 minus 2 is 1. So then the hole would be at x is equal to 3, y is equal to 8. Those are the coordinates of the hole. Once you have the simplified version, you can then, using that simplified version, you can look for the zeros of the numerator and zeros of the denominator. The zeros of the numerator will be the x-intercepts of the graph. So in that case, that would be at x is equal to -1 will be the x-intercepts, and the zeros of the denominator are the vertical asymptotes of the graph. In this case, that would be at x equals 2. So we have one hole, one x-intercept, one vertical asymptote. We also always need to check for horizontal asymptotes, and there's 3 possible cases. Each case is depending on the degree that the numerator and denominator have. If the degree of the top is greater, you will have no horizontal asymptotes. If the degrees are equal, the horizontal asymptote is the ratio of the coefficients as a horizontal line, and if the degree of the bottom is greater, the horizontal asymptote is y equals 0. In this case, the numerator and denominator are both degree 1. So in this case, we're looking at case 2. And the horizontal asymptote will be at y equals the ratio of the coefficients, which is 2 over 1, or y equals 2. Let's go ahead and graph this function while we're here, since we've done most of the work. And as we graph, I'm going to show you a method that I, again, discussed in class about plotting using signs instead of using test values. Okay, I paused the video and I went ahead and plotted everything we just described, the whole vertical asymptote, horizontal asymptote, and x-intercept on a grid. The whole is not quite to scale, but everything else should be to scale. I couldn't make it to go up to 8. So now I need to start plotting the graph by testing some values. And the way you'll do that is by creating a little number line beneath your graph. And on that number line, you're going to put what are called the boundary values. The boundary values are any vertical asymptotes and any zeros, but not any holes. The boundary values are specifically values where the graph could be changing from positive to negative, or above the x-axis to below the x-axis. And the only time that can happen, thanks to, I think, our friend the intermediate value theorem, are the vertical asymptotes and the x-intercepts. So you put those on the graph at -1 and positive 2. And then you'll notice that the number line I drew has been cut into 3 regions. One to the left, one in the middle, and one to the right. We need to test where the graph is going to be in these 3 regions. But instead of actually plugging in values, we can think about just the signs, S-I-G-Ns, of the function in these 3 regions. So I'm basically going to imagine plugging in a value. Like I'm going to imagine plugging in x equals -3. If I imagine plugging in -3, it would be 2, -3 plus 1 over -3 minus 2. But instead of like actually plugging in those numbers and simplifying, that seems like a lot of work. I'm just going to think about what the factors would be. So it would be 2, and then -3 plus 1 is a negative number. So it would be 2 times a negative number over -3 minus 2 is another negative number. So I'm just going to write like a negative in parentheses. Well, I have a negative over a negative, which is a positive, times a positive 2. which means that you the whole net sign of this would be a positive. And I just write like a plus with a circle around to say this is the net sign of a 2, a negative, and another negative. What that means is that in this region of the graph, what I draw needs to be above the x-axis. So I'm going to highlight or shade lightly. If you don't have your highlighter, you can just shade lightly with your pencil. The idea that the graph must be above the x-axis on this side and not below, because the net sign of that function was positive. Now we're going to flip to the middle region, and we're going to pick a test value. And a test value here might be, test value 0 is always a good test value. Now 0 is pretty easy to plug in. You could just plug in 0 and that's okay. But if you don't want to do that, you could still say 2. Okay, and then 0 plus 1 is going to be a positive number. On the other hand, 0 minus 2 is going to be a negative number. So I have 2 times a positive over a negative. That means the net sign is negative, because a positive over a negative is a negative. And that means that between negative 1 and 2, the graph must cross the x-axis and be drawn below the x-axis. Then finally, I'm going to test a value above 2, maybe 4. Just hypothetically, what happens if I hypothetically plug in 4? Well, it would be 2, and then 4 plus 1 is 5. That's definitely positive. And 4 minus 2 is 3. That's definitely positive. So I have 2 times a positive times a positive. The net sign is positive, which means the graph will go back to being above the x-axis here. I also have some further evidence, which is that I have a hole up here, and that will help. So in this case, the hole is also going to be a valuable piece of information. Okay, so with this idea of the sign of the graph, now we can plot it. Because starting at the intercept and moving to the left, I need to go up, not down, and approach that horizontal asymptote. And starting at the intercept and moving to the right, towards that pink vertical asymptote, the graph I know can't like bounce or anything, because I've now shaded the negative side. I know the graph has to go down. Similarly, I know there's no intercepts over here. The graph can't touch 0, so it couldn't be down here. I also know it has to touch that hole, so I'm pretty sure that the graph has to, from the hole, stay positive and go off this direction. And I think that would be a pretty good graph of this function, other than the hole not being quite to scale because it couldn't fit on my screen. But the key idea here is I didn't actually plug in any values except for the 0 and the hole, that I already had. I just thought about the signs of each factor and then computed the net sign in every region on the graph. And that's the approach I'm going to use for the rest of this video as I go over the classwork problems. All right, welcome to the next part of the video. Just look at that highlighted statement. Watching this video is not a substitute for actually grabbing your pencil and grabbing some graph paper and doing the problems yourself. Please pause right now and actually do the work first, and only use this to check, or if you're stuck, or if you'd like another method. Otherwise, you're just doing math by a spectator sport, and math, as we know, is not a spectator sport. All right, let's get right into it with problem 57. So I'm going to start going pretty quickly here. I know that I see there's no holes because there's no terms that cancel. Everything's already factored. I know that the horizontal asymptote, they're equal degrees, so that's going to be at y equals 1. The vertical asymptote is going to be at x equals 2, and the x-intercept is going to be at x equals 0, because that's what would make the top 0. Go ahead and plot all that out. Can't decide how big to make it. There's the horizontal. Here's the vertical. This is really similar to the last one. I have an x-intercept actually at 0. And when it's x equals 0, it's also y equals 0. Now I'm going to plot with signs, and I feel like this is going to be very similar to the last one, but just to check on the method of plotting with signs, I construct a little number line underneath. I plot the two boundary values of 0 and 2, and I need to test hypothetical values. So hypothetically, if I'm testing maybe -2, I would have a negative on top and a negative on bottom. So the net sign would be a positive, which means that on this part of the graph, I will have to be above the axis but below the vertical asymptote. I know it's below the asymptote because I have a 0 right here. Between 0 and 2, say at x equals positive 1, I would have a positive on top, and 1 minus 2 is negative, so I'd have a negative on bottom. So the net sign is negative, which means the graph is going to be down here. And then finally, over here at maybe, let's plug in 4. I know I'll have a positive on top and a positive on bottom, so the net sign will be positive. I also know I have no intercepts here, so the graph should not be in this region. So most likely the graph will be up here. With all of those regions shaded, it's now easy to sketch the graph. Something like that would be an excellent sketch. If you gave me that, I'd be totally happy. Let's go to the next one. 2x over x squared minus 4. So we're starting to get more complicated factors here. I do need to factor the bottom here. So this is 2x over x plus 2, x minus 2. No holes. The horizontal asymptote, it's now degree higher on the bottom, so the horizontal asymptote is y equals 0. The vertical asymptote are going to be at x equals positive or negative 2 from the zeros in the denominator, and the x-intercept is at x equals 0 from the numerator. Let's sketch all that out. So especially when the horizontal asymptote's at 0, this method of checking with signs is going to be really, really nice. The x-intercept is at 0, so we'll plot that here. So we are going to touch and probably cross the horizontal asymptote. And again, remember, it's okay to cross a horizontal asymptote in the middle. It's more of a long-term trend. As long as your function trends towards it on the left and right, you can cross the horizontal asymptote over. All right. We're going to construct a little number line beneath the function and put all the boundary values on the number line. Doesn't really need to be that long of a number line, but make some space. So we'll put -2, 0, and 2. Those are the only places the function can change sign. And now I'm going to look at the net sign of all 3 factors here. So if I plug in, say, -4, I would have a negative over a negative times a negative. I'd have 3 negatives because each of the factors in the original function would be negative. 3 negatives multiplied or divide together make a net sign of negative, which means the graph in this, not quadrant, but this region has to be down here below the x-axis. Between -2 and 0, maybe at -1, I would have a negative factor on the top. I would have a positive because the x minus 2 factor, or -1 plus 2 is +1. Positive, but -1 minus 2 is negative. So I would now have a positive and 2 negatives. That will be a net sign of positive. So the graph in this region will be above the x-axis. If x is 1, then I'll have a positive over a positive, but 1 minus 2 is still negative. So that would be 2 positives and a negative. That's a net negative. So the graph would live down here. And then finally, over to the side, maybe at x equals +4, I'll have a positive, 2 times 4. 4 plus 2 is positive, and 4 minus 2 is also positive. 3 positives is a positive. So the graph will be back to above the axis. Now that I know the only x-intercept, I know there's no other x-intercepts, I know 2 asymptotes, a horizontal end behavior, and where the graph should be, you can complete the picture. There's one branch. This branch has to, starting at the 0 is often easier, go to the left upwards and go to the right downwards. And on the right side, the graph should look like that. So that would be a good graph of this function. Just based on testing values, I didn't plug anything in. You don't have to for me. The specific y coordinates, other than maybe the y coordinates of holes, don't really matter. Also, I would say I'm showing you the sign trick because I think it's easier. If you would like to plug those values in and get the actual numbers to plot, feel free. I'd encourage it. It takes a little longer, but if you're like not sure what's going on with the signs, I'd rather you just plug in numbers and take a little longer than trying to like learn a new trick that you're not comfortable with. On to 61. So first step is factoring. 2x squared is fully factored. The bottom is x plus 1, x minus 1. This x squared is going to change the shape of the middle piece. So that's going to be something we need to pay attention to when we make our sign chart. Holes, there are none. There are no holes because nothing cancels. The horizontal asymptote is also going to be different because we now have balanced degrees. We have an x squared over x squared. So that's going to be at y equals 2, the ratio of the coefficients, 2 over 1. Vertical asymptotes are going to be at x is equal to plus or minus 1. So no holes, vertical asymptotes, horizontal asymptotes, and are we going to have a 0? Yes, it's going to be at x equals 0. These are the 4 things you should always look at before you even start a graph. You don't have to do them in that order, but you should always do those 4 things before you even attempt to construct your graph. Okay, vertical asymptotes on the 1s, horizontal asymptotes at 2, 0 at 0, no other zeros, and no holes. So there are now 3 boundary values. I guess that's similar to how it was before. So we'll construct a little number line beneath the graph somewhere. And on the little number line, I'm not going to use most of it, but I will plot these 3 values, -1, 0, and 1. And I need to think about the sign of the factors between these. I'm going to copy the equation down here so that I can just kind of zoom in on the little number line before I go back to the graph. So I'm now just zooming in on that little guy. And I'm going to pick test values in each of these regions. So we'll start with maybe a test value of -2. That would be on top. Ooh, I would have 2 times -2 squared. Notice how when you square a value, that will always contribute a plus sign, even though the factor is negative. So I'm going to say on the top of the fraction, I have a positive. You can think about it as a negative times a negative if you'd like. I'm just going to say to myself, that's always positive on the top. On the bottom, -2 plus 1 is negative, -2 minus 1 is negative. So net sign is positive because I have positive over 2 negatives. Okay, now I'm going to flip here and maybe test -1/2. This is one I really don't want to plug in. So the sign approach is going to be really nice. If I test -1/2, well, I know the top has to be positive because it's something squared times a positive 2. The bottom, -1/2 plus 1, is positive. -1/2 minus 1 is negative. So the net sign is negative, less than 0. Going to the other side of the axis, let's test +1/2. Okay, so on the numerator, it's still going to be 2 times a +1/2. 1/2 plus 1 is positive. 1/2 minus 1 is still negative. And notice that actually this sign of little sign chart has stayed the same, so the net sign here will be negative. Now let's go over to the right, maybe plug in 2 as a test value. You'll have a positive on top times 2, and then both of the denominator terms are positive, so the net sign is positive. So now my graph has a different pattern. It's net positive, negative, negative, positive. So as I shade in the sort of like region where the graph should be, I need to take that into account. So let's shade in green here. So I need to be above the axis. Since it's above the axis and never touches the axis, there's no zeros there, actually needs to be all the way above that horizontal asymptote. But if you wanted to plug in the actual 2 value in C, you could plug that in. I guess I should just shade and say it's positive, positive. Here, I know the graph is negative. Sorry, zooming out. And negative. And then the graph is back to being positive. So I'm shading in sort of where the graph can be. Now when I go to draw the graph, this is where I'm going to think about the asymptotes. On the rightmost side, is the graph going to be up here or down here? Well, if I think about it for a second, if the graph was below that horizontal asymptote, like it did this, then it would have to come down, cross over, and be negative for a second before it reached the vertical asymptote there. That can't happen. The factors don't have an extra 0 there. That's impossible, at least in this picture. So I need to get rid of that. And by process of elimination, if I can't be below that asymptote, it must be the graph above that asymptote. And it must look like this. A similar situation is happening on the right. The graph could not do this, because if it did, there'd be another intercept, and I know there isn't one. So instead, the graph must do this, or something very close to it. Now, a lot of times people say, oh, I've got my graphs. There's my 2 branches of the graph, and they forget what's going on in the middle. But we shaded a region right in the middle, and we have an x-intercept here. Now, because I've shaded only below the axis, I know that if I go to the right from that intercept, or left, I should say, I should be going down. And if I go to the right from that intercept, I should also be going down. So by shading the graph in those regions, I've found where the graph has to be. Just like I said, I'm pretty comfortable with these, so testing the sign value was enough. But if you weren't sure, say you're like, I need to know a little more confidently that this is above the axis or exactly where that is, then there's no shame in actually plugging in like 2, for example, and just doing 2 times 2 squared over 2 plus 1 times 2 minus 1, and figuring out the value. In this case, that's 8 over, just 8 over 3, which is around 2.6. Did we get it about right? Yeah, it looks like we got it about right. So that would be another totally okay thing to check if you wanted to. You might choose to just check a couple values, and then if you're confident about what's going on in the middle, maybe you'll just check the signs. That's something you can do too. On to problem 63. We need to factor fully. It's already factored fully, so there's no holes. No holes. The degrees are 1 on the top and bottom, so you need to look at the coefficient. In this case, the coefficient is negative 1 over 1. So the horizontal asymptote is at negative 1. We'll say y equals negative 1. The vertical asymptote should be at x equals negative 1 because it's a 0 of the denominator. And the zeros are at x equals 0 yet again because we just have a single x on top. I feel like a lot of problems have had that going on. They don't all have that situation going on. It's just a common situation that makes sort of simple graphs. And so we're trying to keep graphs simple, at least at the start here. Plot everything out. No holes, horizontal at negative 1, vertical at negative 1. Let's make a little number line and test some signs. So you put the boundary values, negative 1 and 0, and probably have a guess about what this graph will look like, but let's just check the boundary values. So the equation is negative x over x plus 1. So if I test maybe negative 2, well, that'd be negative 2. Actually, I'm not plugging in the number. It's negative times a negative 2. So I'm just going to write negative times a negative over negative 2 plus 1 is still a negative. So I have 3 negatives, so the net sign is negative. And I'm just going to, that negative on the x is just going to contribute a negative to these little sign diagrams every time. So here I'm testing between -1 and 0, so that's something like -1/2. Well, that's still a negative times a negative on top. On the bottom, -1/2 plus 1 is a positive. So now I have two negatives over a positive. That's a positive. And if I go to the right of 0 and test maybe something like 1, I still have a negative times a positive, and 1 plus 1 is a positive. So now the net sign is negative again. So now negative means below. Remember that negative means below the x-axis, not necessarily below the horizontal asymptote. So I'm going to shade that whole region for negative. Here I'm going to shade above the x-axis, and here I'm going to shade below the x-axis. But I know that the graph will obey the horizontal asymptote. Just need a little more space here to sketch the graph. The graph is going to obey the horizontal asymptote, and so that shading is going to inform where I draw the graph. It will be easiest to start at the 0. Moving maybe to the left, the graph has to go up because that we know is positive there. And the graph has to be down because we know the graph is positive there. And instead of passing, you should obey that, hit that horizontal asymptote. On the other side, we know the graph can't do this, because if it did, there would be another intercept. So even though I've shaded everywhere below the axis, the graph actually has to be below that asymptote. Has to be. If you're not sure, just actually plug a value in and get a y-coordinate. But I'm pretty confident, so I'm not going to plug the value in and save that time. I know the value is below the axis. I know it has to hit all those asymptotes correctly. The graph looks like this. Pretty confident. Let's go on to the next one. All right, finally something interesting. When I say interesting, I mean something that I need to factor. So there's just a 2 on the top. On the bottom, x squared plus x minus 2 should have factors x, x, 1 positive, 1 negative to get a -2. I guess I need a -1 and a +2. So, no holes. The horizontal asymptote has to be at y equals 0 because the bottom has a higher degree than the top. The vertical asymptotes have to be at x equals 1 and -2 as the zeros are the factors. And the zeros, none. There are no x values that make the numerator 0. Let's sketch all that out. Bottom heavy. Asymptote at 1 and -2. No zeros. So when I make my little number line, my little test region, I'm only going to include the asymptotes because those are the boundary values where the function can change from positive to negative. I'm going to sketch a little number line beneath the graph. There it is. I'm going to put on there -2 and +1. And I need to test 3 potential regions of this graph is all I need to test. So when I make the sign chart, I'll recopy the equation. It's 2 over x minus 1, x plus 2. And then I'm going to make a little diagram of the sign of test factors. So if I test -3, I'll have a positive 2 on top over a negative, and -3 plus 2 is still negative. So the net sign will be a positive over 2 negatives is positive. If I test maybe 0 is a great value to test if you can, if it's not like already an intercept or something. So let's test 0 as a test value. We'd get a positive over well, 0 minus 1 is negative, and 0 plus 2 is positive. So we'd get a net sign of negative. And if I test like 2, we'll get a positive on top still. And we'll get a positive times a positive. The net sign here is positive. So shading in the net signs, I know the graph, I've been using red for this. The graph must be above, below, and then above. I also know it never touches the x-axis. So at least on the outer points, pretty sure this is what has to happen. Probably has some symmetry here. This feels like a relatively symmetric graph. You can try to make them look the same. And on the bottom, I feel like something like that has to happen. Now, I'm not sure exactly the scale, so I actually do kind of want to plug in 0. I feel like if I plug in 0, I can get some useful information. So I am going to still plug in the value. I'm going to plug it into the unfactored version. That seems easier. It's then 2 over 0 squared plus 0 minus 2. Oh, that's negative 1. So I know that f of 0 is negative 1. I can plot that on the graph as a point. Now from this point, I'm pretty sure that what I saw was going to be true, and the graph is going to do something like this. My guess is the 0 is not the actual turning point of the graph, so I'm not going to pretend that it is. I'm just going to make the graph look something like that, sort of centered between the asymptotes. That thing is not actually a parabola, because parabolas don't have any asymptotes, but it's, I guess, parabolish is what you could say. I'd say this is a pretty reasonable graph of that rational function, even though it had no intercepts to graph. All right, moving on, 71. Again, something interesting because there's something to factor. X squared plus x minus 6. So I need to have an x plus 3 and an x minus 2. So I almost had a hole, but don't get excited and cross out terms that shouldn't get crossed out. I just have these things here. So, no holes. Horizontal asymptote. It's bottom heavy. The degree on the bottom is more, so that's going to be at y equals 0. The vertical asymptotes are going to be at the zeros of the denominator, x equals negative 3 and positive 2. And the x-intercepts, or zeros, are going to be at x equals negative 2, because those are the zeros of the numerator. We're plotting all that out on a grid. Something like this. Horizontal asymptote. Two vertical asymptotes. A 0 at negative 2. That looks correct. Let's go create our sign diagram. And there are, again, 3 regions of the graph to test. I'm going to copy the equation down. X plus 2 over x plus 3, x minus 2. So I have 3 values on my sign diagram, so I have to test 4 different regions. We'll test maybe negative 4. So that would be a negative factor on top over a negative factor times a negative factor, so the net sign, 3 negatives, is negative. Now, testing maybe negative 2.5, we can be a little more careful here. Negative 2.5 plus 2 is still negative, but plus 3 flips to positive. Minus 2 is still negative. I have a positive 2 negatives. That's a net positive. Testing 0 again. 0 is just such a nice value. Why don't we just plug it in? If we plug in 0, it's just going to be 2 over negative 6, so negative 1/3. And importantly, that's negative 1/3. And let's test 3. So that's going to be a positive. 3 plus 3 is positive. 3 minus 2 is positive. That's going to be a net sign of positive. So I know from this that the graph needs to start out negative in this region, be positive in this region, negative in this region, specifically hitting negative 1/3 at 0 because I plugged it in and checked, and then positive, be a little more precise, positive in this region. Okay, that's all the evidence we need to sketch the graph. From the left we have to approach the asymptotes like this. In the middle, we need to go up to the right and down in a little curvy fashion to the right like that. Did I say right before? I must have said meant left. And then on the other side, there's no intercept, so I know the graph can't do any of this. Just has no choice but to exist like that. And that's the graph. Next one. All right. So again, we have a factoring situation. So this we have x squared plus x minus 12, so we should have an x plus 4 to get the plus x and an x minus 3, so we get a 12. And this is going to be x plus 2, x minus 2. Again, watch out for factoring and wishful thinking factoring. Nothing cancels. Sadly, we have no holes. We're going to have a lot of other stuff, though. We have a horizontal asymptote equal degrees, so we have a horizontal asymptote of y equal to 1. Vertical asymptotes. We have two denominators, so we have a vertical asymptote at x equals plus and minus 2. And we have two zeros at x equals negative 4 and positive 3. This is really starting to get interesting. Being organized is going to help a lot in our sketching. Put that right here. Horizontal, 1. Vertical on the 2's. Zeros at 3 and negative 4. So the graph almost looks symmetric, but the zeros already are not quite on center, so there's going to be a little bit of asymmetry here. Let's figure out what's going on with the graph by making our little sign diagram. Put the boundary values on, negative 4, negative 2, 2, and 3. Now I have actually 5 regions because I put 4 marks on the number line, so there's 5 regions to test. We copy down the function, x plus 4, x minus 3 over x plus 2, x minus 2. Hopefully we are starting to think carefully about the factors and noticing that when all the x's are positive here, and I pick a value, there's no like weird coefficients going on, and I pick a value to the left of negative 4, like negative 5, all of those factors start out as negative. So, pick negative 5 over here. Well, plus 4, that's still negative. Minus 3, that's definitely negative. Plus 2, that's still negative. Minus 2, definitely negative. So all 4 factors end up negative, and then 4 negatives times each other and then divided gives you a net positive. At negative 3 as a test value, negative 3, yes, that works. Notice that only one of those factors should have flipped sign. Everything else is going to stay the way it was. And the factor that's going to flip sign is the factor that you just crossed over on that line. Notice that negative 3 plus 4 is now a positive factor. But everything else, negative 3 minus 3, still negative. Plus 2, still negative. Minus 2, still negative. Everything else stays the way it was. So 3 negatives and a positive, that's a negative. Now let's check 0. So now I've flipped over the negative 2, so I bet that this x plus 2 factor is going to turn positive, but let's check. 0 plus 4 is positive, 0 minus 3 is negative, 0 plus 2 is positive. Yep, that thing I expected to flip did actually flip. 0 minus 2 is negative. 2 positive, 2 negatives, that's a net positive. Between 2 and 3, so like maybe 2.5, 2.5 plus 4 is positive, minus 3 is still negative, plus 2 is positive, and minus 2 is now positive. That x minus 2 factor flipped to being a positive factor. So that's going to be a net negative. And then over to the right of 3, maybe at like 5, all of those numbers are less than 5, so all 4 of the factors should be positive, 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 positive. The product of 4 positives is a net positive. So the graph I can see now goes from positive to negative to positive to negative to positive to negative. Positive, negative, positive, negative, positive, and stop. Said too much. Let's shade that in. So the graph is going to have to be here, positive, flip over, be negative. In this region, there's no intercepts. The graph is entirely positive between the asymptotes, which means it has to be above that horizontal asymptote. I mean, it could be here, but there's not going to touch the 0. I guess I'll shade in that region. It could be there. And this could be up here, but it's not going to be. Then over here, we have negative. This little bit is going to be just negative for a little while, and then it has to flip to positive for this entire region. Now, we can fill in like where the graph goes. So you have to hit that 0, and you have to obey the two asymptotes, so the right-hand side needs to do this. The left-hand, did I say right again? Left-hand side. The real right-hand side also needs to have a 0 and an intercept and do this. Finally, the middle piece, it might help to plug in 0. F of 0, again, would just be everything would be 0 except 12 over 4. So f of 0 is negative 12 over negative 4, which is just positive 3. So we could go up here and say, okay, f of 0 looks like 3. I don't have any more intercepts. There's nothing there, and the graph is entirely positive. So most likely, the graph does something like this, and maybe not quite symmetric. I don't know. It doesn't have to be perfectly symmetric. You could plot some other points if you wanted to. I think that's a pretty reasonable graph based on the evidence that we have. And then, finally, our last graph of the day. Thanks for sticking around if you've been watching the whole thing. I hope you enjoy graphing these. I do. I actually like it. It's satisfying to see everything come together. We have some factoring, some serious factoring to do. So let's see what can be done. Okay, so I paused to double check my factoring. You could approach this with the AC method on the top, or grouping, or just plain old guess and check. Since there's no factors of 4 that also have a 3, then you know the 3 and the 4 have to be in the same term, and then just kind of guess and check from there. The bottom just has a common factor of x that pulls out. Nothing cancels, no holes. But we do have some intercepts. So first let's do the asymptotes. The horizontal asymptote is going to be at the ratio of the coefficients because the degree is the same. So it's at y equals 3/2 or 1.5. Vertical asymptotes are at the zeros of the denominator. So that's at x equals 0 from the x term and x equals 5 over 2 or 2.5. That's the 0 of 2x minus 5. Also, we have zeros. We have one at x equals 1 from the x minus 1 term, and also one at x equals 4 over 3, or 1.3 repeating from the 3x minus 4 term. So nothing really is changing in this problem other than there's annoying fractions. Don't be afraid of the annoying fractions in factoring, but it certainly makes this problem a little bit scarier to approach initially. Plot the horizontal asymptote at 3/2. I am going to use my line tool just to make it easier. So the asymptotes will be in, we've been doing them in pink. We'll keep them in pink here. Vertical at 0 and 2.5. Close enough. We have zeros at x equals 1 and x equals 4/3 or 1.3. So real close over here. Okay. What a mess of a graph. Let's check some things out. Let's check some values. I'm going to try to do this without the aid of a calculator, just using that idea of the sign chart and which factors are flipping signs where. Make a little baby number line underneath our graph. We put on that number line the boundary values. So the boundary value is 0. We have a boundary value of 2.5. We have a boundary value of 1 and a boundary value of 1.3. And the equation I'm looking at is x minus 1, 3x minus 4 over x, 2x minus 5. Okay. So when I plug in something like -1, we get a bunch of negatives. Everything's negative. So we have a negative over a negative times a negative over a negative. Shoot, well, 4 negatives actually makes a positive. Now let's plug in a test value like maybe positive 1/2 and see what changed. Well, 1/2 minus 1 is still negative. 3 times 1/2 minus 4. 3 times 1/2 isn't going to be bigger than 4. That's still negative. 1/2 is now positive. That term has flipped sign. 2 times 1/2 minus 5 will still be negative. So we now have 3 negatives and a positive. That net sign is negative. Now I need to test, I'm going to draw a little arrow, a value between 1 and 1.3. I don't know, how about 1.1? This is annoying, I will say. This is an annoying way to test. 1.1 minus 1 is positive. 3.3 minus 4 is still negative. 1.1 itself is positive, and 2.2 minus 5 is definitely negative. So now I have 2 positives and 2 negatives. That's a net sign of positive. So between these two values, the graph will be positive. To the other side here, we can just test like 2. I'm drawing some arrows to just make more space for the work here because they're all so close together. If x is equal to 2, we'll have a 2 minus 1 is positive. 3 times 2 minus 4, so that's now positive. Positive, but 2 times 2 minus 5 is still negative. So I have a net, 3 positives and a negative is a net negative. And over here, if I test something big like 3, 3 is not that big. 3 minus 1 is positive. 3 times 3 minus 4 is positive. 3 is positive. And 2 times 3 is 6, minus 5 is 1. That's still positive. So notice, again, I don't care what the whole fraction value is. That would be some really frustrating tiny number. But I'm thinking about each factor one by one, deciding is that factor positive or negative, and then computing the net sign of those terms. So I had 4 boundary values, which means I have 5 different net signs to compute. Here they are. I'm going to shade them on the graph using this handy highlighter that I had. So I have positive, negative, a little negative region that's only 1 unit wide, then a little positive region up here between those 2 zeros, a little negative region here, not being super precise with my shading because it's just a tool, and then a positive region over here. Clean up that shading too. Well, that should actually be enough to sketch the graph. Let's do the middle piece first. That seems the most logical. It seems like with these 2 zeros and with what's positive and negative, from this 0, we have to approach the asymptote, flip over, just turn right around, and turn back down like this. I don't know the exact shape. Exact shape doesn't matter. It's an ugly sketch, but it's a good enough sketch. Over here, on the right, the graph can't do this because there'd be another intercept, so the graph has to do this. You could test a value if you wanted to. I don't feel like I need it. Same over here. The graph can't touch the axis again, so it has to do something like this up there, and there's the graph, and it's 3 branches together based on the boundary values. So that's all of that work in one. Well, we're approaching 50 minutes. That's a long video. If you sat through it all, thanks for watching. It was like a whole class. I hope it's been helpful. Please let me know what questions you have. Please study these functions. Other than maybe the annoying fractions in the last one, everything you see here could easily have appeared on a quiz or test. These are definitely within the realm of expectation of things I want you to be able to do. Also, none of these problems had any holes other than the introduction. Make sure that you could do these also plotting any hole values, H-O-L-E hole values, if you had them. All right. Thanks for watching. I'll see you all next time.